So today is an exciting day, and we are in the last session for this semester. And over the weekend, we took some quality time to distill down the amount of material that you would need to cover for this last module, because we wanted to give you an easy button as you approach the last few days of this week, and then you look on into your exams next week. So in terms of the calendar, I thought it would be important for us. Let's review this while we're at it. Let me capture the attendance now that we have another person who's joined us. So can everyone see the calendar?
Yeah.
Yes.
Okay. So I'm going to basically cover the remaining concepts that we didn't cover last week in Module 4 today. And then I'm going to review with you the two short assignments. So we have two like shotgun assignments. So we took basically the content from two different modules and created an abridged study guide. So you have just 8 pages to review. And you'll want to take the first attempt at your Module 4 assessment by 11:59 p.m. this Saturday. So after we finish walking through the remaining concepts on these 8 pages, you're going to want to study it a little more. And you're also going to want to complete the short assignments, the quick assignments, also by the end of this week, by 11:59 p.m. Saturday. So a little bit of study, some quick assignments. Take your first attempt at Module 4. If you need more time to finish assignments, we can easily allow you to finish those next week. Your Module 4 solution will take a little longer than the quick shot assignments. So when I say a little longer, I expect that your solution would take all of 1 hour. So you would watch a video and then you would repeat the steps of the video. So we're talking, let me repeat that, 1 hour for your final solution, right? So we're getting down to the finish line. We don't want to stress anybody. I'm going to post that tomorrow so that you can have a look at it. But I'll try to get it out today, but I'll have it out by noon tomorrow at the latest. You have through the end of exam week, 11:59 p.m. December 5th, to submit the solution or to finish any of the retakes for the assessments. So basically, you want to finish review, try your first attempt at Module 4, do some quick assignments by 11:59 here. You can take your retake assessments anytime this week to help you prepare for your final exam, and you'll have to have your final exam done by the 11:59 p.m. on the 5th. You can also turn in your last solution by 11:59 on the 5th. Are there any questions about the timelines for what we have to get in there yet?
No, I got it.
Okay, so quick shot solutions would probably take all of 20 to 30 minutes if you have a quiet place to focus. And one of the things that we want to call out as a distinction is this idea that there are two branches of statistics, one that's descriptive and one that's inferential. And so the descriptive statistical methods are largely very concrete, and they're calculation oriented, and the inferential methods are predictive. And so the statistical hypothesis is not the same as the scientific method. So when we talk about the scientific method and what's important for your experimental method, there tends to be an overemphasis. So why did we have this student learning objective first? Relate the scientific method essentials, including the relevance of meticulous records. It's everybody gets nuts about the numbers. I don't know what it is, but everybody's focused on grinding out the statistical analysis. And then the whole point of an experimental method, though, is to be able to repeat an investigation, to share your results with the world. And oftentimes when people simply try to repeat something, it ends badly because they don't spend a little quality time to record the non-numerical things. So I wanted, as we brought our semester to a close, to kind of come full circle. We talked early in this semester about how, logical decisions and taking the time to think about inputs and outputs when you're doing custom programming, those types of considerations, those quality considerations. People tend to get into the weeds of doing the actual work for the experiment, and they get all worried about the statistical results. And unfortunately, what happens is that when it's time for somebody to try to repeat and validate the results, they can't, because they just don't have the basic information. So this is common sense, but it is part of scientific computing applications and doing them effectively and doing them well. So, in section A, I talk about the difference between an Erlenmeyer flask and a round bottom flask. And I think last week I asked if anybody had been in chemistry or in a previous session. So let's say you did something in chemistry and you had an Erlenmeyer flask. Does anybody know the difference between the shape of the bottom of that flask compared to Erlenmeyer and round bottom?
Is one not like wider in terms of like circular?
Yeah, I mean, round bottom is basically a perfect globe, right? But Erlenmeyer is flat. So if you're laying it on a heat pad, on a hot plate, which one do you think is going to heat more evenly and more quickly?
The Erlenmeyer.
Absolutely, right? Silly stuff like that. So you get all these results, you get all this data and outputs, and we tend to forget. It's all about the calculations. It's all about the math, right? No. You want to be able to duplicate things. And then when somebody, see, actually what happens, this field of study is very well developed. Descriptive statistics and inferential statistics, that's not going to be the breaking point, or that's not going to be the problem area. When you have something important to share with the world, that's not going to be where things break down. That's actually pretty straightforward. And even if you do modeling, right? Now there are conventions about modeling, and we'll get to that in a minute. And we'll talk about Monte Carlo and Markov chain and a few other things for modeling. But basically, it's the other non-intuitive stuff that gets everybody into trouble. The last thing we want to cover are the two common adaptions. So when you're working with experimental data, especially large data or unstructured data, the common method to manage very large data sets, we'll talk about sampling for a minute, and then something called NoSQL. So you have these new methods like JSON, where you have very unstructured data. If you end up having to work with experimental data, and so that would end our concepts here for module 4. Oh yeah, and we talk about scientific methods. So here's another thing that happens all the time, and in Dr. Ratchford's presentation, it just hit me like a brick, because he spoke it so clearly and so well. Everybody's focused on the hypothesis. So in the same way people get if they get fixated on the statistical numbers and the outcomes, they also get fixated in terms of scientific method on this hypothesis. And that hypothesis is only an answer. So if you have an answer to a question and you think it's right, by extension, you should be able to prove the hypothesis by inferring a prediction. Well, what am I saying? Well, if you have an answer and you say, oh, I know that when the temperature gets too warm, that's what's killing the coral. So I'm going to predict that if we observe coral in seawater above this temperature, I'm going to predict that the coral dies within X amount of time. People are fixated on the hypothesis or the research question and the informed answers. And what needs to happen is the extra step. You have to take the extra step to infer a prediction that you can use to design the experiment. So what am I saying? You only design an experiment based on the prediction, not on the hypothesis. You're going to have a question on this for our assessment and on the final exam, because this is one of those fixations again. Everybody gets all about the scientific method, but when it comes down to the actual scientific computing piece and the data, if you're going to have solid results, you need to design your experiment around proving or disproving the prediction, not your hypothesis. Okay? So you extend and take some quality time to develop this idea of a prediction that's measurable, quantifiable. How can you, if your hunch and your answer is correct, how can your prediction be structured in a manner that's quantifiable and measurable? And that's where the design of the experiment takes off. A lot of people get hung up and they just take a whack at it, right? They take these educated guesses and then they try to prove their educated guess. Don't take the shortcuts, because what you're going to get is garbage. If you take shortcuts, then you're going to waste your time, right? So we just wanted to be sure by the end of the course that people understand. How do you make this happen, right? How do you take care of this first student learning outcome, right? If the intent of this first piece of our module, if you want to have any professional credibility as a researcher, you design your experiment to prove or disprove the prediction. And you want to take a little time to journal meticulously all of the experimental concepts and tasks, especially the ones that can be quantified in terms of your prediction, right? What kind of measures are you using? How finely graduated are they? Have they been, what's the word I'm looking for? Have they been calibrated recently? Okay, a lot of times people don't even think about calibration when they're measuring. When they do the statistical analysis, their statistics are all over the map. And they think it's, oh, the math is wrong, the computing application is wrong, all that, the tech is wrong, right? Okay. We spoke about this last week when we reviewed some of the slides from Dr. Ratchford's presentation, that there are two types of data in terms of statistical analysis that is not to be confused with the data types in a programming language, right? So you have discrete data types that are cleanly defined into categories, and then you have the continuous data types, and that helps you use the cheat sheet. Is this ringing a bell with people? The cheat sheet?
Yeah, the command cheat sheet.
Right. So if you're using inferential statistics because you want to determine a relationship between data sets or populations, the thing that I wanted to call out here that wasn't quite so obvious, if you have an independent variable So I actually outline the steps that you should follow to use this cheat sheet. So one of the things you have to do is identify which variable is independent and which one is dependent based on your experimental design. And I actually go to the trouble of explaining independent variables. So the word dependent, if you can remember, it's hard to keep those straight. I just want to offer you a bit of advice. So the dependent variable is the one that depends on the independent variable. So the variable that's dependent is quite often the independent variable is an input and the dependent variable is the output. So that's one way to think about it. The independent variable is the data element that is intentionally manipulated and controlled as an intentional input. And the dependent variable is the data element that requires a measurement of output. Now, there are elegant scientific design scenarios where that simple statement is not true. I'm just talking in general terms. I'm just giving you a rule of thumb to go by. So as you're looking at the different statistical data measures or types, it's also important to identify which one is the independent and which one's the dependent, and you have to understand, right? So whenever you change or control the independent variable, there's a result that's generated in the dependent variable. And that's one way to look at it. And then this statement here, by changing inputs and measuring the nature of outputs, scientists can more precisely determine and define how a dependent variable does what? Depends upon the input of the independent variable. Now you can have lots of variables in a situation. So oftentimes when you have multiple data elements or factors, what a lot of scientific method centers on is systematically performing input changes for just one of the variables and keeping the other ones constant, right? So this is how we start to delineate or understand how criteria or attributes of a design scenario, how the variables are related to each other. In some cases, they might be proportionally related or inversely related, but one way to distinguish between proportional. The other thing too is that another common mistake that's made is that when people are talking about inferential statistics and relationships, they're always thinking about the similarities between the two populations, and if it's different, they go, oh, there's no relationship there. And a difference is a relationship. A difference is evidence of a relationship, an inverse relationship. So that's the other thing about inferential statistics. You're using probability and you're trying to define this idea of whether or not something is completely random or there's a connection. We're always looking for a connection. Is something related? That's really at the heart of the whole process. And this inferential statistics allows us to prove or disprove what's called that null hypothesis. The null hypothesis, quite simply, is everything's totally random, they are not related. And in the most basic of terms, if there is a relationship between two data sets or variables or populations, there will be similarities, non-random similarities, or differences, non-random differences. And that's another Achilles heel, is that people often forget, hey, if you're seeing a difference and there's a pattern, it's not random. The real trick is whether it's random or not, right? Any questions so far about where we're going with this?
No, not so far.
Okay, so if you see something in red and yellow like this, that's something you want to memorize. So that's the whole point of what we're doing here. And we're going to focus. So I'm distilling 2 modules worth of material down to the core, right? 90 minutes, 2 hours worth of review on 7, 8 pages, right? In inferential statistics, you have this thing called the p-value or error and an R factor. And in simple terms, if the p-value is, that's the error, is less than 0.05, and that's an arbitrarily set, but it's a commonly practiced error level. If it's lower than that, it plainly reflects a case where there's some kind of relationship, meaning it is non-random. So if you want to prove that something is related and not random, you're looking for a p-value that is 0.05 or less. And the tests that we showed you on the cheat sheet from last week are what you'd run to generate your p-value. And in terms of a regression analysis, you have this thing called an R factor. So the R factor is closer to the line. And actually, if you go ahead and take the time to do the first assignment, there's a nifty and very brief definition of all that, and it explains how that works. But when the dots are patterns on a traced line or regression analysis, you trace the line where the data elements appear on the chart. If they're close to the line, the R factor is high. The closer it is to a 1, the greater confidence a researcher can claim about selected aspects of the relationship. But the other thing that we want to call out is the slope. So if there's no slope, then that affirms the absence of a relationship, either proportional or inverse. So again, I'm oversimplifying, but I just wanted to give you some quick details about some of the statistical methods. You can't draw an absolute conclusion with inferential. So you can absolutely draw a conclusion about the average values of a data set or the range of a data set. Those are concrete. That's descriptive statistics. But inferential is all about the potential for, you're looking for the non-randomness. It's all about how random something is, and the less random it is, then the greater the possibility or probability that there is a relationship between those things. You never have causality. So when you're calculating correlation, if you do a correlation analysis, and I'm going to show you that in a minute, one of the things you cannot do in a correlation analysis is declare, hey, this causes that. So you have to take things quite a bit further in order to be able to identify the cause and effect as opposed to a correlation. So has everybody heard of correlations versus cause and effect before?
I have not, or I don't remember that.
Yeah, I have in a previous class.
Okay, so when you're doing your baseline research, when you're doing your seminal, all right, so original research is often called seminal research, right? So it's original. Once you identify dependencies and correlations, right? You identify relationships, non-random relationships. Then you refine your experiments, and the design of an experiment at that point changes, because you want to move away from inferential statistics, and you want to identify a cause and effect. You want to be able to state. And so this is something that the state of California does very well, right? And just thought so if you live in California, is there anybody in our class that formerly lived in California or lives in California now? And you're just here for like a program? Anybody?
Nope.
Nope. Okay, so the state of California conducts many health and safety experiments to keep their population safe. And there's a lot of warning labels on products, and they're sold in the state of South Carolina or used in the state of South Carolina that by law have to be labeled. This substance is known by the state of California to cause cancerous tumors in laboratory rats. That's not correlation. We've gotten past the point of proving a non-random case when we prove cause and effect. So yeah, and based on the scope of our last module, we're only focusing on correlations or non-random relationships at this point. But I wanted you to be aware of where that leads. Okay, once you identify something as non-random, you've discovered, oh my gosh, when this environmental variable is playing out, then laboratory rats have cancer, right? There's a correlation between the number of, and what's the correlation? Is it different? Is it a different correlation, meaning it's inverse? Oh, when this environmental factor is present, the number of cancerous tumors in laboratory rats decreases. It's actually a pattern. It's non-random and it's different. So as that element in the environment increases in prevalence, the number of cancerous tumors decreases, right? That's an inverse relation, just a difference, right? Not a similarity. Or if you had another substance, right? UV exposure, for example, or certain toxins. Benzene is a great example. Has anyone ever seen the movie Erin Brockovich?
I've heard of it. I
Yeah,
don't know. It might have been from you, actually.
yeah. So the power company out in California, make a long story short, they were doing things with their operations that put more chromium-6 ions in the environment around certain communities. And they had horrible rates of cancer and birth defects. They had a really hard time pinning that down. They first started with correlations, right? They did studies and they started to correlate, and eventually they got to the point where they understood a cause and effect. Then they went to court and they sued and they won a $330 million lawsuit against the power company. It's a landmark. The movie is a true story, and it's actually a really decent movie. But anyway, all right, so getting down to the chart, right? Let's get back. Any questions before we go on? Any questions?
No, no question for me.
Okay.
No questions from me.
No.
Okay. Now we have one less person now for some reason. We won't worry about it. Okay. So here it tells you by the numbers. First thing you do is identify which variable is independent and which one is dependent. Then determine of the data element used, is it discrete or continuous? So is the independent, I may tweak that and this will become revision 1A because I'm not real jazzed about that sentence right there. But anyway, revision 1A. You're going to determine with the independent variable and then with the dependent variable, which type of data, is it discrete or continuous? So step 3, select the appropriate column based on the independent data type. So in a given scenario, and I'm going to do this, I'm going to give you a simple scenario where I tell you, and I'll even tell you, you know, you have 2 variables and this one's independent and that one's dependent, and here are the measures. And you need to be able to look at the scenario and say, oh, this one's continuous or that one's discrete, right? Because it might be something very simple with the discrete, like male and female or yes and no or whatever. Certain age bracket, right? Senior citizen, that's a discrete age bracket. It's a category. Senior citizen is anyone over the age of 65, I think, by definition, right? Stuff like that. So once you have that variable and you figure out which one is dependent or independent and then what type it is, just start with the independent variable and go to which column. The right one if it's continuous, the left one if it's discrete, right? So select the appropriate column and then select the appropriate row based on the data type of the dependent. So that's when you come to the row. You come over to this side now and you say, okay, it was discrete and now it's going to be the dependent variable is continuous or the dependent variable is discrete. The thing I want you to know is that I'm going to try to trick you on the test, probably at some point, and say you have a continuous independent variable with a discrete dependent variable. What common test do you use for inferential statistics according to the cheat sheet? And you know what you're going to tell me? Nada. Nothing. There is no quick and easy. Okay. Now, let's digress for just a second to this block right here. Can everybody see this one?
Yeah.
Okay.
Yeah.
So what are you going to do for your assignments, the quick shot assignments? Well, you have two fast, lightning tasks, right? Where you do descriptive statistics, and all you're doing is reading up on how to do it, and then you do it. Nothing fancy. 5-minute read, watch, and then do it. Another 5 minutes. So in the first case for, let me get this up here. So in the assignment that you see right now on Blackboard, and by the way, the inferential statistical assignment is going to be out there after our class is over, about sometime between 2 and 3 p.m. Okay, so you're basically going to do two things, two quick tasks. So Excel has an add-on that does all this for you. So what am I saying? You walk through the steps, and in 5 minutes or less, you have a set of scores. So in each case, I'm giving you the numbers like we did last module. You don't even have to type those in, right? All you're doing is opening the CSV file. It'll have scores and it'll have the numbers ready for you. And you follow the steps after you look at the tasks on a web page or watch a video. And all you have to do is highlight and select the options, and it does a full workup of all the common descriptive statistics that most people have to generate. So, everybody's familiar with means and averages and standard deviations. I do go into a lot of trouble. There'd be another reference and a little walkthrough on variance and standard deviation, how you calculate that. But basically, if you just do it, and you look at the, where are we? Oh, the study guide. Yeah, I'm here. Sorry. In the study guide, we talk about, in the section up here, we talk about the descriptive statistical analysis. So you have this normal distribution of data. Typically, the data can vary. There's a description for a lot of natural populations that refer to a standard deviation, how much the data changes. Depending on the population or the things that you're studying, you might have a very steep curve with very narrow and thin base, right? Which they'll sometimes call the tails or whatever. But so the green is here, the red is thinner and taller, and then the blue is flatter with wider edges, wider, thicker edges. So that's referred to as the kurtosis. So how tall and thin it is. And then if there's a slant, that's called skewness, right? So that tells you how the distribution of results or data points varies from a normal curve, right? So if you have a standard deviation that normally traces, you know, how do your results differ? These are all very quantifiable in concrete terms, in hard numbers, and doing it manually sucks. And I feel sorry for people who have to take statistics courses where they're doing it manually. I'm just saying. The whole point of scientific computing applications as a course is to find out how to use the easy buttons, and you have an easy button and it takes a few clicks and there it is all for you. It's all calculated. It tells you the kurtosis, it tells you the skewness, it tells you the range, the min, the max, the sum, the number of samples, the standard error, the standard deviation, all of that. Woohoo! I love that. So each of the tasks for your 2 assignments work pretty much in that manner. Let's go back to the assignment document. So here is the link that you go to do the descriptive statistics first. And you may find that you might have to copy the link, but so you're going to do a box and whisker plot. There's a separate set of steps that you're going to follow on the screen with the assignment document for box and whisker for the second part. But for the first part, you're going to have the CSV file that you import, and that tells you what to do and where to find it. And all you do is follow along, and then you take a screenshot and you post it. It's just that quick. Now, let's talk about the inferential assignment, right? When you do the inferential assignment, can everybody see this right here?
Yep.
So quite often in our experimental scenarios, you have continuous measures with independent variables and continuous data for the dependent variables. And in that case, you're doing a regression analysis or a correlation analysis. You're gonna, so box and whisker is what you're doing for, you're gonna use the descriptive analysis, I mean the descriptive workup, and then box and whisker for the descriptive assignment. So it's 2 parts, box and whisker and descriptive statistics. And then for the inferential assignment, you're going to do a correlation analysis and a regression analysis. And where are you going to do that? Well, I found this website, and oh man, I wanted to throw a party because it does a better, quicker, more efficient job of explaining how to do this stuff. So if you're ever in an experimental scenario where you have to generate a histogram or a graphical representation of your data, or like we said, statistics or ANOVAs, right? So ANOVAs are like mini t-tests in combination when you have 3 or more variables that you're trying to assess together. If you had just 2, you would do a t-test. If you had 3 or more variables you'd have to analyze, you'd do an ANOVA test. In any case, correlation and regression, you're going to basically follow the steps in the same fashion. I'm going to give you the information. You can import the CSV, open it up, and away you go. And after a couple of steps, you're done, right? That's it. So all you're doing is following the screenshots and clicking, and you're done. to perform a regression analysis correlation, right? It's basically going to walk you through a set of steps, the same fashion. I'll set the stage for you, so all you're doing is performing the tasks to generate the result. What is that? 6 steps. Click OK, and here's your result. 6 steps. This is a game changer. A few years ago, just 2 years ago, there was a much more manual and rigorous and guided process you had to go through to do this. I just want you to experience just how quick and easy some of this stuff is, and how painless it can be. So, are there any questions about what's expected for the second assignment? You're doing regression analysis, correlation analysis. Everybody understand?
Yep.
Okay.
Repeat that one more time.
Say again?
No, I was gonna, you could repeat that one more time.
So for your first assignment, you're going to do descriptive statistics and a box and whisker plot. So when you're working up a box and whisker plot, that is a graphical representation of statistical results that falls into the descriptive statistics category, right? And it's not inferential, but it helps you see visually what you're getting from the descriptive statistics result. So you're going to click on this to read up a little bit about it, and then you follow along here. And for the box and whisker, there's going to be a walkthrough. So there's a YouTube video. I think it's how long is it?
The owner of a restaurant wants to find out more.
8 minutes long, right? What's not to like? 8 minutes long. Watch the video, then do it. And so all you're going to do is take the CSV file that I provide you and follow these steps here. So instead of having the web page to follow, you're going to generate your box and whisker. And what you should get is something that looks like this, right? So when you're creating a box and whisker diagram, right? This line represents the range of values in your data set, and this box represents where most of them lie. It's kind of like the bell chart. It's like the bell curve in miniature. So where are most of your data, where do most of your data results lie in terms of value within the box? But you have some that are as low as 1 here and some that are as high as 22 here. So the line shows the range of values, right? How much they vary in total from minimum to maximum. But then this also gives you an idea of where most of the data points fall in the box. That's the point of a box and whisker. So it gives you like a condensed, sort of a condensed graphical representation of a chart of the results, except you don't have to go to the trouble to work this up. It's another graphical representation, and it uses the output of the descriptive statistics add-in that Excel has now that's free to use, and it generates that result. And it's just as quick and easy to do as the other exercise. okay? So you're going to get a result, except it's going to be your first initial and your last name, a box and whisker. You're going to click on the title and replace chart 1 or title 1 with your name and that. Any questions?
Nope.
Okay. So let's talk a minute about the solution. So when I post the solution, you'll need to watch a half-hour video, and the individual that does this talks fast and works on the screen fast. And I would advise you watch it once through, and then well, basically what you're going to do is generate some large numbers. So let's talk briefly to close about modeling. So when we're measuring actual experimental results and modeling. So we're talking about modeling. What we're doing is taking a method that we would use for regular experimental analysis, but instead of using actual values, we're going to substitute. And in simple terms, what you're going to do is use artificial results for the purpose of prediction. So after actual measures and statistics prove to be very reliable and consistent, then you can use that same calculation, that same analysis with a different range of inputs to predict what happens if the values vary outside the norm. And that's a layman's description of it. But basically the last two sections here of our study guide, it's about what if scenarios. So you're going to take something that works in a plain sense, and then you're going to use a whole series of artificial values. The key is random numbers. So when you're modeling, it's important to be able to generate random numbers. So one of the hottest fields in scientific computing right now and in mathematics is the ability to generate completely random number sets. And there's a lot of reasons why you'd want to do this. Many times an experiment in the physical world is not very practical, or it's just impossible. Nuclear weapons testing used to happen in the real world, and the number of cancer cases started to spike quite a bit for a number of years until people started to correlate and then actually prove a cause and effect. Hey, you know what? The more above ground tests we have, the more people get cancer. And then, so they put it underground and they started using nuclear weapons testing underground. Well, guess what? People actually are affected by the environment, by the quality of the underground in our world. We have things like drinking water and soil substrates and agriculture, and there's a whole variety of complex relationships. But basically, before long, they figured out, you know what, we can't even do it below ground. So what they did after running so many tests and establishing so many clear and well-defined relationships, they started generating very large random number sets. So one of the things I want you to understand is that when it comes to scientific computing, the ability to work with large random numbers and authentic random numbers. When you're generating artificially random number sets, the computing algorithm is actually not so random. So what computer scientists have figured out is that you have this issue. Once you have those large number sets, you can plug them into high performance computing methods like matrix computing, where the calculations are performed in a distributed fashion, or in cluster the same way they're distributed. Or you can use actually gaming cards, video gaming cards. They have this, they have a RISC-based processor that's very good at floating point calculations, and the same thing that allows gamers on networks doing like Xbox, Halo, right? And I'm just trying to think of all the cool stuff that people work with now. Those same graphics cards can be teamed together, and you can actually have the computing power of a Cray supercomputer that used to cost $10 million 25 years ago in a workstation that sits in your house with 2 gaming cards. And I'm not making that up. But in any case, when you're talking about random numbers, you're talking about petabytes of data, because you want to run lots of iterations, millions of cycles of calculations, so that you can see whether or not the model holds true. When you do your solution, you are generating some random numbers to perform a Monte Carlo simulation, but you're going to step through it in Excel, and it's something that you can easily do within 45 minutes. And so I just wanted to explain a little more about what's going on there and why we're doing Monte Carlo, right? You also have other simulation models that are very popular right now, like antithetic and control variates. Some of this is in your textbook: PRNG seeding, importance sampling, and Markov. What do you need to know for your assessment or for this module? Just when you see those terms, you want to know that those are modeling and simulation methods, right? If I say ANOVA, you should be able to say, oh, that's inferential statistics. That's not modeling. If I say Monte Carlo, you're going to say, oh, that's a modeling method, right? Everybody with me?
Yeah, so far.
Okay. So give me 30 seconds and we're done. When you have huge data sets, one of the biggest problems is that, well, a lot of times you're working with a computer system that can't process all of that gargantuan data, right? So one of the methods to cope with modeling and simulations, one of the limitations of data analysis, is that even though you want to work with very large data sets, sometimes it's not practical to work with very large data sets. So you perform sampling. That's one of the workarounds, sampling. What's most important about sampling is that it's random. So just like generating random numbers needs to be an authentic, randomly authentic, like the same kind of randomness that would occur in nature. Your sampling process and which data elements you choose and the algorithms that you use to sample also needs to be random. So what's the common thread there? Large random number sets is used for modeling, and what else? Oh yeah, random. When you're sampling, because you have too much data, you need to randomly sample the data if you want to have a credible result. You also have this case where data sets are not neatly defined into tables where the data tables were normalized. Much of the world now doesn't know the first thing about Cod and his relational algebra. And so you have these large data sets that are unstructured, and you have to be able to work with them. Basically, there's this NoSQL movement. And so you're using tools like Hadoop. There's a whole class of really weird sounding NoSQL unstructured database tools. So I'll probably have like special topics, 2 paragraphs to flesh that out a little bit, but JSON is one of the methods. BSON and JSON and Hadoop. There are a couple of NoSQL tools that you can use to work with unstructured data. I just wanted to introduce those topics for you. That's it. That's all we have for the last class of the last topic of the last concept. for scientific computing applications. Are there any questions before we close?
None from me. All good.
Okay, well, I hope everyone has a pleasant and enjoyable Thanksgiving break. I wish you well on your retakes of the assessments and on your, and I would brush up on the reconciliation. If you reconciled your previous assessments, just have a look at that, and then good luck with on the assessment retakes. And I hope that helps prepare you for your final exam. And remember, you have plenty of time all next week to take any of the retakes and to finish your solution and to get your exam done. And then for this week, all you want to try to do is take your first attempt, and then on module 4, and then get the 2 quick assignments done. Okay?
Okay, and for the final exam, how is that going to go again? How are we going to take that?
When your final exam is scheduled to be available based on the UVI official schedule, it will be online, but the window to complete it will stretch through the end of the week, 11:59 p.m. on 5 December.
Okay, so we can gain access to that on Blackboard, right? That's how.
Yes, if you need to take it on the prescribed day and time, it will be accessible and available to you.
Okay.
Okay, if and that, everybody's schedule is different. So some people, want to get it done sooner because they have other exams later in the week. So everybody's going to have to plan accordingly, which is why we didn't want to throw too much material or have too lengthy in terms of assignments. We wanted something that was manageable, right? So, but that's, yeah, it'll be out there, but you don't have to take it at that day and time. And it's not a proctored exam. I am not watching you. You don't have to load Respondus. What you will have are a lot of questions from all of the assessments. You won't have time to look up stuff. So if you don't brush up before you take your final, you might know some of it off the top of your head, and then you're going to find out that 2 hours is not a lot of time. Okay. Does that answer your question?
Yeah, it does. I was just making sure I knew where to find it and how long we had to do it and all that.
It'll be on Blackboard, and it'll be in this section right here, cumulative exams.
Okay.
When the exam period starts, we're going to pull these other, I'm going to have another module available called retakes, where you can still access the retakes, but nothing else. So be sure, if you want to download anything off of the Blackboard, that you get it before we hit the exam period, because once we start exams, exam conditions are in effect, which means I'm going to pull the modules, except for any assignments or other assessments that people want to take for preps, right? So you'll see retake assessments and cumulative exams when the exam week starts next week, instead of modules 1 through 4. Okay.
All right, sounds good.
All right. Well, take care, and good luck, and we'll see you on the other side of the holiday. I'm going to stop sharing.
All right, thanks. Have a good one.
Yeah, you too.
Thanks. Bye.
Bye-bye.
Have a good one, everybody.
Enjoy your Thanksgiving.
All right, you too.
Bye-bye. Stay safe.